Well, hello everybody, and welcome to Digital++. This is a brand new playlist which is focused on the practical side of AI and machine learning. This means we're not going to go into the mathematical background of machine learning. We're going to look at the practical aspects of implementing it. Ultimately, I want to use AI to support building out our metaverse. And for people interested in that, you can watch my previous videos of how to build a metaverse playlist. This AI playlist is really standing on its own, and it can be viewed without the need to really follow my earlier videos. This episode provides an introduction of how machine learning works, and we will build and test a very simple model that can determine whether a person on a picture is male or female. For that, we will use Jupyter Notebook, we will use Python and Tensorflow, and we will build and test the model. First, let's do a little bit of R&D, and let's roll up our sleeves and get into the weeds. So how does a artificial neural network work? Well, an artificial neural network is modeled after a human brain. And a human brain consists of neurons, and neurons are brain cells. And brain cells have a number of inputs, and then they have a cell, and then they have an output, which is then going to the next level of neurons. An artificial neural network, therefore, consists of what we call a perceptron. So a perceptron is like a cell which has a number of inputs with weights, and then it applies a bias, and then there's an output, and then it's going to the next level. So you can combine all those into what we call a basic artificial neural network. And an ANN always has the same structure. It has an input layer, and it has an output layer, and a bunch of hidden layers in between. Data flows from the input layer to the hidden layers to the output layer, and those flows are what we call tensors. So how does a artificial neural network learn? Well, we can go into a lot of theoretical detail here, but the practical thing you need to understand is that within this perceptron, as I said, you have weights, so every input has a weight, and a perceptron has a bias. So the artificial neural network learns by identifying what the weights and the biases are for all of its perceptrons in the network. So neural networks can approximate any convex continuous function. And a convex continuous function is something like you would see over here, the blue arc, right? So a convex function is kind of a hollow function. It has an optimum somewhere and it's continuous. So there's no like gaps in between. And a neural network has been mathematically proven to approximate any possible convex continuous function. So let's see what are stages of machine learning. When we want to learn an artificial neural network something, it's all about identifying the weights and the biases, right? So before you do that, you need to prepare all your data so that it actually, your ANN does understand what is it looking at and make sure that the data is suitable for it to understand it. Then you build a model. The next step is you train and validate the model. You fine tune and iterate that a number of times. And then once it's done, you get a model and trained parameters. And those together identify your machine learning model. Once it's accurate and you think it's right, you can actually apply the model and let it predict things. And that's what we're going to do as well in the next couple of slides. Data preparation, how would that work? Let's have a look. So what we have, for example, in our situation, we want to create an artificial neural network that can recognize faces and identify whether a face in the picture is a male or a female. So first of all, we can download the dataset. There's people have done a lot of work already on creating datasets. The data is not just the image itself, but each image also needs to have a label. So every image needs to have a label whether or not this person on the image is a male or a female. So you can download a lot of datasets with that labeled data already readily available. And in some situations, you may need to create your own data set, but that obviously could be a lot of work. Before you can actually start entering data into a machine learning model, you would need to split it. So you need to have training data and you need to have validation data. Validation is crucial because you can train your model on data but then you may just train it to recognize data it has only seen before. But obviously you want it to recognize data it hasn't seen before yet. And that's why validation data is crucial. So you're not training the model with validation data. You're just using it to validate to see whether or not the model is properly generalizing. So let's look at the machine learning model as a complete black box. So you see the black box with the blue brain there. Inputs are all floating point values somewhere between 0 and 1. And the output is also a probability-ish something between 0 and 1. So you need to squeeze all your data into zeros and ones so that your machine learning model understands it and it spits out zeros and ones again. So if you want to use that, you need to then change it back into images, bytes, or whatever. And so let's have a quick look on how that would look in our situation. So you have your images here. There's 64 by 64 pixels, for example, and you have tens of thousands of images, and you push that into an array. In this situation, how do you squeeze a picture into a neuron? Well, you flatten it, so you have 64 times 64 is 4096 pixels, and every pixel is 1 byte. And let's assume the picture is now grayscale, because you could probably recognize whether somebody's male or female with a grayscale picture, right? So now you have 4096 pixels and bytes. So, but obviously that's not a value between 0 and 1 yet. So you now need to divide it by 256 so that you get a value between 0 and 1. And that's now a floating point, and you can put that into your model. Usually in machine learning, we say the data itself is a capital X, right? So your input is X. And then your labels, which are male, female, those are also 0 and 1. You call those Y. So your capital X is the input, the Y are always the labels. And you could have multiple labels, obviously, but in our situation, each image has one label, male or female. And then the machine does a prediction. Initially, it has learned nothing, so it just spits out a probability. Well, I think the probability that this person is male is probably 50%, and I think the probability this person is female is also 50%. Yeah, well, that's not so great. The probability that it's male should be 1, and it should not be 50%. So there's an error in the output. There's a process called backpropagation where we go backwards in the model and we update the weights and the biases of the model to cover the error that was made, and that's what we call a loss function or a loss. We go backwards into the model, and then if you apply all this data again multiple times, so after multiple sequences of pushing all the images through the model and doing backpropagation afterwards, you see that the model starts to improve its learning and the predictions start to become much more and more accurate. Now, every time a complete set of data is pushed through this black box, that's what we call an epoch. And typically you would train like 30 epochs or so. So 30 times you push the whole training data set through the model. Now, unfortunately, as I said, if you just push the training data, there's not a lot of value in it because it will only recognize the pictures that were in the training model, and it would never recognize a completely different picture, like somebody's camera picture or so, right? So that's why we have the validation data, and we do find something very similar. So we may not have 10,000s, but maybe thousands of these images. We flatten them again, we divide them by 256, their inputs, the label, it's either 0 or 1. It's input Y, it predicts, and then it spits out the probability for male or female. So the validations go alongside with the training cycle, so they follow the same epoch sequence, but you see there's no backpropagation in the validation data. So it doesn't learn from the validation set, it only checks whether or not the model has sufficiently generalized so that the validation data is equally accurate as the training data. And we'll see a very good example of that in the demo that we'll do in a bit. So yeah, we measure the loss at the end of each epoch, and then we don't do any backpropagation. Let me move myself out of the way a little bit. What you then typically see is the image over here where the blue line is the performance of the model on the training data. Horizontal scale here, you see the number of epochs, so the number of time we've pushed all the data through the model. On the vertical scale, you see the loss or the error, and you see the error gets smaller and smaller and smaller, and ultimately it gets pretty close to almost an error of 0. But you see that the validation data is much less accurate and it has a much bigger error and it doesn't converge that much. So how would we use a trained model? Now let's assume we've gone through all of this and we said, okay, well, it's now accurate enough, we'll just use it. So you have all your weights and your biases and you have the model definition, and you can save that into a file. And that file you can store, and then you can call it later on and use that to predict new images. So again, you now have a single picture, for example, 64 by 64 pixels, and you flatten it again. You again do exactly the same. You divide it by 256. You send it an input. You say, well, this is a female, so I'm expecting the output of 1, and then you ask it to predict, and then the model then thinks this is probably a female. And that's how you would use a model. Let's do a little bit of design work. Let's build a simple gender DNN model. And I said ANN before, so what's the difference? Well, a deep neural network, that's what a DNN stands for, is a network with multiple deep layers. And a deep layer is anything between the input layer and the output layer. And yeah, we can basically play around with how big these layers are, and I'll show that to you in a bit. So we'll build a simple deep neural network to determine gender from a picture. So you see on the top right, cut out of this data set. It's a huge amount of data, and each image has a number of labels. Each pixel is 200 by 200 pixels, and they're all RGB color. The labels, they're part of the file name prefix. So we need to extract the label from the file name. And we'll see how that works in a bit. We will convert the images in the pre-processing. So we'll first resize them from 200 by 200 to 32 by 32, and then we will change it into grayscale. We do that obviously to reduce the dimensionality and the amount of memory required, and also the training speed. The DNN, it will be extremely simple. So it will have an input layer, which is mandatory. It'll have two deep layers of about 300 neurons, just randomly picked, and it will have an output layer of about 2 neurons, for example, male and female probability. How does that work? So let's have a look here. We have a 200 by 200 pixel image, and that's about 120 kilobytes. We resize it into 32 by 32, so we have about 3072 bytes. Then we only take the grayscale factor, so it's only 1024 bytes. So we flatten it to 1024 bytes, we divide it by 256, and now it becomes 1024 floats. But how it exactly works, that every single pixel of the image, so all 1024 pixels, are fed into each neuron. So that means that each neuron in the input layer has 1024 inputs. And then the neuron feed into the next layer. So the next layer of 300 neurons will see 300 inputs, and that's obviously each of the outputs of the previous layer. And then the last layer in our case will be 2 neurons. The one is for the male and one is for the female output. Therefore, you only have 2 neurons. Each neuron will have 300 inputs. That's because the previous layer has 300 neurons. How many learning parameters are we talking about? And we have all the 1024 pixels here, which are all the inputs. So that means that in the first layer, each neuron has 1024 inputs. So that is 1024 times 300. That's a total of 307,200 weights of inputs. Each input of a neuron has a weight, and that's one of the parameters we need to learn. We also said that each neuron in the layer has a bias, so we need to add those. So we need to add 300 biases. So the first layer has 307,500 parameters it needs to learn. Let's go to the next layer, very similar. So each neuron has 300 inputs, so 300 times 300 is 90,000 weights. But we need to add 300 biases again, because the second layer also has 300 neurons, so that will be 300 biases plus 90,000, so that's 90,300 parameters it needs to learn. And then the last layer, 2 neurons, has 300 inputs, so that's 600 weights. And then we need to add 1 bias for each neuron, so that's 2 biases obviously, so that's a total of 602 learning parameters. So the total learning model has 398,402 learning parameters. Note that with the original 200 by 200 color image, you would have already 36 million parameters. And that's just a 200 by 200 pixels, so you can already see this doesn't really scale that well, this model. But okay, we'll come back to that in a bit. All right, so we've now gone through the parameters in the model, and now let's go into Jupyter Notebook and start building, see how that works. Okay, so I've opened up a clean, empty Strawman Jupyter Notebook. Now this episode does not cover how you set up Jupyter Notebook or how you set up the GPU, but let me know if you have interest. We could always see if we can squeeze in an episode which talks about how to set that up and how to configure it. But for now, I'm assuming you already have this installed and configured if you want to follow along. In this first cell, we need to get all the libraries. We need to have operating system because we want to have access to our directories. We need NumPy, and NumPy is a table library that helps us with managing matrices and tables. We need matplotlib, which we will use to create plots and images that we can show. We will need CV2. CV2 is a library to load and save images, and it's actually OpenCV. And we need Tensorflow, obviously. This is a one that's called toCategorical. I'll explain that later on. Last but not least, we will also need something from the sklearn library, and that is the function to split your train and your test data. So let's run this. All good. All right, so now we're going to define some variables and arrays. So we first of all need to have a place where all of our data is. For this tutorial, I'm going to use the UTK face dataset. You can download that and then just install it into your directory. It's a whole bunch of pictures of people, starting with young people. The further you get, the older they are. There are male, there are female people in there. It's about 20-ish thousand, as I said in the slide. Each of these images are 200 by 200 pixels. The label of the image is embedded in the file name. So you see here 73. Means that this person is 73-year-old. One means it's a female, etc. Let's create an empty NumPy array to load all the images into. I also want to have an NumPy array for the labels, male or female. Now I'll create another one to convert the labels into categories. One for male, one for female, and that's why I am going to convert this gender table into a gender C table, which has two columns, one column for male and one for female. We need a batch size. That's one of the parameters that we have that we can change. So standard, I'm always using 32 for now. Image size, and that's also a parameter. So for now, I'm going to scale down all the images to 32 by 32 pixels. We'll see how that looks like later. We'll need a parameter for the number of times we're going to run the training set. It's called epochs. For now, we'll do 30. And I'm going to the helper table that helps us convert the male and female into a readable string. So now the next step is that we're going to read all the images into the NumPy array. For each file f in the directory, we are going to take the second argument of each of the file names, because we know the second argument was the indication whether you're male or female. Then we are going to create the image, and we'll do that this way. We do a CV2, and then we do an imread, and we read the path, and then what we also want to do is read the grayscale version of the image. At the moment, it's still 200 by 200, so now we are going to resize it to image size, which is 32 by 32, but again, we can change that later on if we want. And then we're going to append the file that we just read, and we'll do exactly the same for the labels for the gender. So this is basically the X data, and if you look in the slides, and this is the I labels. And then last but not least, we are now going to convert these arrays into NumPy arrays as well. So let's do the following. So we now have the images and the gender array, and we're going to explicitly cast them to a NumPy array. So let's do a run. It'll take a few seconds because it has to go through all the 20-ish thousand images and create the internal arrays. So I'll pause for a second until it's done. So we've now loaded our images, and let's have a quick look how that all looks like. So you see there's 21,345 images, and they're 32 by 32 pixels. All right, so that's how it looks like. So let's do a quick view of how one of those images looks like. So plt.imshow, well, let's take image 20 in gray. So let's see how that looks like. There you go. So yeah, it's you see it's 32 by 32 pixels. So we see this is a picture of a male person and a little bit younger of age. So if you squint your eyes, you could probably figure out whether this is a male or a female. Awesome. All right, let's look at a little bit more. I'm going to copy paste all of that in now. What we're going to do is look at about 40 pictures just to give an idea of how the data set looks like. So let's do that. Here we have 4 rows, 10 columns, and do an offset so you can play around a little bit and go through the data set. So this is a mix of mostly females. Let's go to 25, see what that looks like. And so you can see the picture here and the label above. So it does show the whether or not somebody's male or female based on the label that we read from the data set. And so now we're going to use this data to input into our to-be-built AI model. All right, so let's go through preparing the data set. So what I said earlier, we had 2 label arrays, a gender and a gender C. So how does that work? So the gender data currently is 0 or 1. And if you're 0, you're a male. And if it's a 1, you're a female. female. So you can use that to create a prediction. But then what if somebody accidentally puts in a picture of a bear or a horse? And the outcome would be a 0 or a 1. So it would still try to estimate whether you're male or female. So I'm going to use a categorical approach, which means now we have not one output, it has two outputs. The first output is probability that you're male. The second output is a probability that you're female. So if you would put in an image of a bear, you would expect that the output for both of these would be 0, right? Because it would neither be a male nor a female. So what we're going to do here is we change the data set of the labels into a categorical data set. All right, so let's do that. And now we're going to split our sets. So as I said in the slides, you need to have a training set and a validation set or a test set. So we call that train and test. Oh, actually it should be train and validate. Maybe, sorry, let's do that. So validate. And so this is the sklearn library that helps you with at random splitting your data set. And then what do? Well, we want to have the images and we want the categorized column of the gender. So let's do that. Let's have a look at what xtrain.shape looks like. You see this one is 16,000 by 32 by 32, and then the remainder is about 4,000 or 5,000 validation images. So we're now going to scale the data sets, xtrain and xvalidate, train divided by 255. 255. Then the next step we do is, well, we create a model. So we say our gender model is a sequential model. We're using Keras for this model. We're going to add an input layer. So we need to specify that always. So the first layer that we're adding is an input layer. And we know that the input shape is image size times image size. So the next layer is that we're going to flatten the input layer. So we add a flatten layer. Now we're going to add a 300 node dense layer. And we're going to use an activation function called ReLU. I'm not going into the details here. Each neuron needs to have an activation function, right? A ReLU activation. If the input value is lower than 0, then the output is 0. And if the value is higher than 0, then it is the output value. So basically cuts off all the negative values. And then we're going to add another layer like this. So the second 300 nodes, like we said in the slides before. And then we're going to add the final layer, which has 2 nodes. This time we're not going to use a ReLU, but we're going to use a softmax activation function. Yeah, the activation function in the output layer always needs to be aligned to the type of output that you have. And because we have categorical data, we need to use a softmax function. And now we're going to compile the model. So we do gender model, compile, optimizer is Adam. And we need to provide a loss function, right? Because it needs to learn. And because we use categorical data, we have to use categorical cross entropy. So let's try that. That works. All right. So let's do a summary of the model. So let's have a look how that looks like. We have a flatten layer. We have a dense layer. We have another dense layer of 300 neurons. And then we have a layer of 2 outputs. And if you look at the numbers that I showed in the slide before where we calculated the number of parameters, you see this exactly matches the calculation I had on the slides. Adds up to a little under 400,000 parameters. All right, so we are now ready to train the model. So what we do here is we clear the backend session just to be sure that no garbage is left in the system. And then we collect all our data in an array called history gender. And we do a gender model.fit, which is our training function call. And we feed that with xtrain and ytrain, and we validate that with xvalidate and yvalidate. We use the batch size, well, 32, as we defined at the top, and we do it for 30 epochs. So let's run this and see how this goes. Cool. All right, so you see each training cycle takes about 2 to 3 seconds, and that means each epoch, all of the images will be pushed through the learning model. And after every batch size, which is 32, the parameters are all updated. So the biases and the weights, and we do a back propagation. And we do that until all the data is done. So after 30 times that all of the images have been passed through the system, we will stop the learning. We're almost there. Okay. So now all of the weights and the biases have been adjusted. What you could do now is save the model so we can use it somewhere else. But let's first look at the data and see how it looks like. And we say, well, we want a picture of about 10 by 3. Then we want to show the loss function. So we want to see in one color what is the loss data. So let's call that training loss. And I also want to see the validation loss. Let's draw the legend and then let's plot the whole thing. So the blue line is the loss function, the training loss. So with the number of epochs increasing, which is here on the horizontal scale, you see that the learning has gone better and better, right? After a while, the training loss was only about 5.22. You see that it continuously improves. We would have been able to train a little bit longer as well. You do, however, see that with the validation loss, with the validation data set, the performance is not that great because you see there's a lot of fluctuation and it's not really improving a lot anymore after about 20-ish epochs, and it's even going up again at the end. So there's definitely what we call some overfitting here in the model, which means that the model works really well with data it has been trained on, but with new data it doesn't behave that well, and that's what we call overfitting. So yeah, this model has some issues, and we'll come back to that in a bit more. Let's do some additional tests to show how it would behave on some complete new data set, which is data the model has never even seen before outside of the UTK data set. And so let's give it some time to read. So it created a new array called images2 and genders2, and we resized it to the right size, 32 by 32, and I've pushed the new images into the model and asked the model that we trained here above to predict whether or not the output would be male or female. All right, so that's now completed. And what it does here, it does show what the gender is according to the label that we provided in this data set, but we also are going to show the predicted data here. So let's run this, and we have about 20 images. So let's have a look. This image, the label was female and the model predicted it was female. The same here, the label was female, the model predicted it was female. So you see, all in all, it's not too bad. Here it made a mistake. So the gender here was female, but my prediction of the model, it came out with a male, and the same here. For some reason it thought this was a male. So yeah, you can see the performance of the model is not too bad, but not too great either, right? Let's say 20 to 30%. So let's do a quick recap of what we've seen. So this model we have built has obviously some limitations, but it was only there for demonstration purposes, right? So this one definitely doesn't scale to larger images. It has many parameters, and it will quickly overload because the structure is what we call dense, right? It has all these dense layers with all these nodes connected to each other. And it's also just not accurate enough. If you see someone's eye, you could probably already identify whether somebody's male or female. So we'll need more advanced features, and you could read layers that could do stuff like convolutions or correlations, and also reduce the number of parameters. So this model is like a one-shot. It doesn't remember anything. It has learned to identify whether you're male or female, but it doesn't remember whether the first 5 people that you've did before were also male or female, or it doesn't remember whether it has seen you before or not. So, and that's something like ChatGPT and large language models can do. And this model obviously doesn't have that. The last thing that this also can't do, it cannot generate anything like, for example, ChatGPT or Stable Diffusion. That's way more complicated. So we go far beyond the scope of this introduction and demo. All in all, this model wasn't too great. It wasn't too bad either. I think it was a great introduction. It was small enough for you to really understand how it works. It still gives you a fairly good introduction of how machine learning models work in general. And this rolls up this episode of Building AI. I hope this was a useful introduction, and hopefully people now have a better idea of how this machine learning works under the hood, or bonnet as they say in the UK. Ultimately, this channel will continue with multiple playlists. As I said earlier in my previous videos, we will continue to have Unity VR coding tutorials, and we'll continue to have user experience videos, and we'll also add more AI videos as we go in this playlist. I hope this was an interesting video for everybody. Please feel free to comment, leave your comments below. If you have any ideas or thoughts, also let me know, and I hope to see you all again very soon. Thank you, and bye-bye.